So here's something worth thinking about as you settle in tonight. Right now, wherever you are, there's probably a computer chip within arm's reach. Maybe it's in the phone on your nightstand, or the laptop you just closed, or that little smart speaker across the room. And inside that chip, there are transistors, tiny switches, packed so impossibly close together that if you could somehow shrink yourself down to walk among them, the gaps between structures would be measured in individual atoms. Not hundreds of atoms, not thousands. Individual atoms. We're talking about distances so small that the rules of physics you learned in school start to break down, where electrons don't behave like little balls anymore, but instead act like ghosts that can pass through walls. And yet, somehow, we figured out how to build these things. Not just one of them, but billions of them on a single chip. And we do it over and over, millions of chips a day, with a reliability that would make a Swiss watchmaker weep. How on earth did we get here? That's what I want to talk about tonight. The whole story, from the very beginning, told slowly. Because honestly, the story of how computer chips are made is one of the most astonishing things human beings have ever accomplished. And most of us carry the result around in our pockets without giving it a second thought. So let's give it a second thought. Or really, let's give it a long, slow, wandering series of thoughts. And if you drift off somewhere along the way, that's perfectly fine. The story will still be here. Let's start where it actually starts, which is not with computers at all. It starts with a material, silicon. And to understand why silicon matters, you need to understand a little bit about how electricity moves through stuff, which, I promise, is more interesting than it sounds. So picture 3 types of materials. You've got conductors, like copper wire, where electricity flows through easily, like water through an open pipe. Then you've got insulators, like rubber or glass, where electricity basically can't flow at all. The pipe is sealed shut. And then there's this third category, this wonderfully weird middle ground, called semiconductors. A semiconductor is a material that's not a great conductor and not a great insulator. It's somewhere in between. And here's the thing that makes semiconductors so special. You can control how well they conduct. You can push them one way or the other. You can make a piece of semiconductor act like a conductor when you want it to, and act like an insulator when you don't. That ability to switch, that's the foundation of everything. Every computer chip ever made depends on that one property. Now, silicon isn't the only semiconductor out there. Germanium works too, and in fact, germanium was used first. But silicon won out for a bunch of practical reasons we'll get to. The important thing right now is that silicon is the second most abundant element in the Earth's crust, after oxygen. It's everywhere. It's in sand. It's in rocks. It's in the glass in your windows. The raw material for the most sophisticated technology humanity has ever created is, quite literally, dirt. There's something kind of beautiful about that. But let's back up even further, because the story of computer chips really begins with the story of understanding electricity itself, and then the quest to control it. In the early 20th century, if you wanted to control electrical signals, amplify them, switch them on and off, you used vacuum tubes. And vacuum tubes were, honestly, kind of amazing for their time. A vacuum tube is basically a sealed glass bulb with the air pumped out, and inside, there are metal elements that can control the flow of electrons through the vacuum. They were the key technology behind radio, early television, radar during World War II, and the first electronic computers. But here's the problem with vacuum tubes. They were big, They ran hot, they burned out constantly, and they used a tremendous amount of power. The ENIAC, one of the first general-purpose electronic computers, built in 1945 at the University of Pennsylvania, used about 18,000 vacuum tubes. 18,000. The machine weighed 30 tons, filled an entire room, and consumed around 150 kilowatts of power. There's a famous story, and the details are a bit disputed, but the spirit of it is true, that when ENIAC was running, it would dim the lights in the surrounding neighborhood. And those 18,000 tubes would fail so often that a significant part of operating the machine was just finding and replacing the dead ones. Some estimates suggest a tube would blow every couple of days, and each time, the whole system had to be shut down while technicians crawled through the guts of the machine hunting for the bad one. So people knew, even then, that vacuum tubes were a dead end for computing. If you wanted to build something more powerful, something with more switching elements, you couldn't just use more tubes. The machine would be the size of a building. It would need its own power plant, and it would never run long enough between failures to actually be useful. What they needed was something that could do what a vacuum tube did, control the flow of electrical current, but smaller, cooler, more reliable, and cheaper. And that's where semiconductors enter the picture. The place where this happened, and I mean the specific, physical place, was Bell Telephone Laboratories in Murray Hill, New Jersey. Bell Labs in the 1940s was one of the most extraordinary concentrations of scientific talent the world has ever seen. It was the research arm of AT&T, the telephone monopoly, and because AT&T was so enormously profitable, they could afford to let very smart people work on very fundamental problems without demanding immediate commercial results. The culture there was remarkable. Physicists, chemists, metallurgists, and engineers all worked in close proximity, and there was this deliberate mixing of pure science and practical engineering that turned out to be incredibly fertile. The key figure to start with is William Shockley. Shockley was a physicist, brilliant and ambitious, and he had been thinking about semiconductor amplifiers since before the war. He had this idea that you could use an electric field to control the flow of current through a slab of semiconductor, essentially using one electrical signal to control another, which is what amplification is. But his early attempts didn't work. The theory said it should work, but when they built the thing, nothing happened. The semiconductor just sat there, stubbornly refusing to amplify anything. This is where two other people become crucial. John Bardeen was a quiet, unassuming theoretical physicist, twice a Nobel laureate, eventually, which is a club with very few members. Walter Brattain was an experimental physicist, a hands-on guy who loved building things and tinkering in the lab. Shockley assigned them to figure out why his field effect idea wasn't working, and what Bardeen eventually realized was that there were what he called surface states, electrons getting trapped at the surface of the semiconductor, forming a kind of shield that blocked the external electric field from penetrating into the material. The electric field was being screened out before it could do its job. Now, this could have been a dead end, but Bardeen and Brattain, working together through the fall of 1947, started experimenting with ways to get around the surface state problem, and on December 16, 1947, they demonstrated something that worked. Brattain had rigged up a delicate contraption involving a tiny wedge of plastic with a strip of gold foil over it. The foil slit down the middle with a razor blade to create two contact points, just a hair's breadth apart, both pressing down onto a small slab of germanium. When they applied a small signal to one gold contact, they got a much larger signal out of the other. It amplified. It actually worked. This was the first transistor. They called it the point contact transistor, and it was, let's be honest, a pretty fragile, finicky device. But it worked. It could do what a vacuum tube did, and it was tiny, and it used almost no power, and it didn't burn out. The implications were enormous, even if the device itself looked like something you might accidentally break by breathing on it too hard. Now, here's a bit of the human drama. Shockley was not in the room when Bardeen and Brattain made their breakthrough, and by several accounts, he was furious. Not outwardly, not immediately, but it ate at him. He was the one who had started this whole line of research. He was the one who had the original vision. And yet, the key invention had been made by his subordinates, and his name wasn't on the patent. So Shockley did something that turned out to be incredibly consequential. He went off on his own, working in secret over the Christmas holiday and into January 1948. And he came up with a different and ultimately better design. The junction transistor. Instead of those fragile point contacts pressing onto a surface, Shockley's design used a sandwich of semiconductor materials with different electrical properties layered together. It was more robust, more reproducible, and more theoretically elegant. And it pointed the way toward how transistors would actually be manufactured at scale. All three of them, Shockley, Bardeen, and Brattain, shared the Nobel Prize in Physics in 1956 for the invention of the transistor. But the relationships between them were never the same. Bardeen eventually left Bell Labs for the University of Illinois, where he'd go on to win his second Nobel for work on superconductivity. Brattain was gradually sidelined, and Shockley's story takes a turn that reshapes the entire geography of the technology industry, but we'll get to that. The important thing right now is what the transistor meant. Think about what that means. A tiny device made from a chip of semiconductor material that can act as a switch, on or off, 1 or 0. And if you can make one switch, you can make two. And if you can connect them in the right way, you can make them do logic. If this and that, then this. If this or that, then this. And if you can do logic, you can compute. Every calculation your computer has ever done, every photo on your phone, every message you've ever sent, every frame of every video you've ever watched, all of it comes down to enormous numbers of tiny switches flipping between on and off, ones and zeros, billions of times per second. And it all traces back to that little slab of germanium in a lab in New Jersey in December 1947. But here's the thing. Having a transistor is not the same as having a computer chip. Not even close. A single transistor is just a switch. To do anything useful, you need lots of them, connected together in specific patterns to form circuits. And in the 1950s, that's exactly what people did. They made individual transistors, packaged them up in little metal cans with wire leads sticking out, and then engineers would solder them together on circuit boards along with resistors and capacitors and all the other components you need. Each connection was made by hand, or at best by semi-automated machinery, and every solder joint was a potential point of failure. Every wire was something that could come loose or break. This was fine when you needed dozens of transistors, or even hundreds. But people could already see where this was heading. The military wanted more complex electronics for missile guidance systems and aircraft. The telephone company wanted better switching equipment. Computers were getting more capable, which meant they needed more transistors, which meant more connections, which meant more potential failures and more cost. They called it the tyranny of numbers. You could design a circuit that needed 10,000 transistors, but actually building it reliably, wiring all those components together without error, was becoming the bottleneck. The transistor itself had been miniaturized, but the way circuits were assembled hadn't kept pace. And this is where the story takes us to a place that, in 1958, was not exactly the center of the technological universe. Dallas, Texas. Specifically, the offices of Texas Instruments, where a young engineer named Jack Kilby had just started work that summer. Kilby had come from an electronics company in Milwaukee, and he was new enough at Texas Instruments that when the company shut down for a mandatory 2-week vacation in July, he didn't have any vacation time accrued. So while almost everyone else was gone, Kilby was alone in the lab, thinking. And what he was thinking about was the tyranny of numbers. What if, instead of making each component separately and then wiring them all together, you could make everything, transistors, resistors, capacitors, all of it, out of the same piece of semiconductor material? What if the entire circuit could be built on a single chip? On September 12, 1958, Kilby demonstrated a working circuit built on a single piece of germanium. It was rough. The components were connected by tiny gold wires bonded by hand, and it looked, frankly, like a mess. But it worked. It was an oscillator, a simple circuit that produces a repeating signal, and when Kilby hooked it up to an oscilloscope, there it was, a clean sine wave tracing across the screen. His boss reportedly looked at it and said, "That's it." And it was. That was the first integrated circuit. But halfway across the country, someone else was working on the same problem, and his solution was, in some ways, even more important. Robert Noyce, at a small startup called Fairchild Semiconductor in Mountain View, California. And yes, that's the same Mountain View that would later become the heart of Silicon Valley, was independently developing his own version of the integrated circuit. And Noyce's approach had a crucial difference. Instead of connecting components with hand-bonded wires, Noyce figured out how to use the same photographic printing techniques that were already being used to pattern transistors on silicon to also print the metal connections between them. Everything, the transistors, the wiring, all of it, could be built up layer by layer on a flat piece of silicon using a series of chemical and photographic steps. No hand wiring, no individual assembly. The entire circuit could be fabricated as a single, monolithic piece. This was the real breakthrough, the one that made mass production possible. And it set the template for how every computer chip would be made from that point forward, a process of building up patterns on silicon, layer by layer, using light and chemistry. Noyce filed his patent in July 1959, and what followed was a long, complicated patent dispute between Texas Instruments and Fairchild that eventually ended with both companies being credited as co-inventors. Kilby and Noyce are both rightly called fathers of the integrated circuit, though their approaches were different, and it was Noyce's planar process that became the foundation of the industry. And now we're standing at the threshold of something enormous, because once you can print an entire circuit on a single chip using photographic techniques, the question becomes, how small can you make the features? How many transistors can you fit? And what happens when you start shrinking them down, year after year, generation after generation? That's where this story really takes off. Because in the early 1960s, the integrated circuits coming out of Fairchild and Texas Instruments were impressive, sure, but by today's standards, they were almost comically simple. We're talking a handful of transistors on a chip, maybe a dozen, maybe a few dozen. The features etched onto the silicon were enormous, relatively speaking, measured in millimeters. You could practically see them with the naked eye, and the circuits they made were basic. Simple logic gates, flip-flops, small amplifiers, Useful, absolutely. But nobody was running a spreadsheet on one of those chips. But here's the thing. People started noticing something. Every year, the number of transistors that engineers could cram onto a single chip roughly doubled. The features got smaller, the processes got more refined, the yields improved, and suddenly you could fit twice as many components in the same area. And this wasn't just happening once or twice. It kept happening, year after year after year. The person who first articulated this pattern was Gordon Moore. And if that name sounds familiar, it should. Moore was one of the original co-founders of Fairchild Semiconductor. He was right there alongside Noyce in the early days. In 1965, Moore wrote a paper for Electronics magazine in which he plotted the number of components on the most cost-effective integrated circuits over the previous few years, and noticed this remarkably consistent trend of doubling. He extrapolated forward and predicted that this doubling would continue for at least another decade. That prediction became known as Moore's Law, and it turned out to be one of the most consequential observations in the history of technology. Now, let's be clear about what Moore's Law actually is, because it gets misquoted all the time. It's not a law of physics. It's not like gravity or thermodynamics. It's not something the universe requires to be true. It's an observation about the pace of engineering progress. Moore noticed that the semiconductor industry was doubling transistor density at a remarkably steady rate, and he predicted it would keep going. Later, around 1975, he revised the doubling period to roughly every 2 years instead of every year, and that's the version most people cite. Every 2 years or so, the number of transistors on a chip doubles. And here's what's wild. It held. For decade after decade after decade, Moore's Law held. Not because of some magical force, but because the entire semiconductor industry organized itself around making it come true. It became a self-fulfilling prophecy in the best possible way. Companies planned their research roadmaps around it. Customers expected it. Competitors raced to keep up with it. The industry created formal technology roadmaps, literally documents that said, okay, by this year, we need to be at this feature size. And by this year, we need to be at this smaller feature size. And here's what we need to invent to get there. Moore's Law became the metronome that the entire industry marched to. But making transistors smaller isn't just a matter of wanting it badly enough. You actually have to solve incredibly hard engineering problems at every step. And this is where the story of chipmaking becomes a story about the relentless refinement of a single core process: photolithography. Remember, Noyce's big insight was that you could use photographic techniques to pattern circuits onto silicon. Well, photolithography is just the fancy name for that process, and understanding how it works is really the key to understanding how every computer chip gets made. So let's talk about it. Picture this. You start with a wafer of silicon, a thin, perfectly flat, incredibly pure disk, maybe the size of a dinner plate in modern fabs, though in the early days they were much smaller, just an inch or two across. This wafer has been sliced from a large cylindrical crystal of silicon and polished to an almost unbelievable smoothness. We're talking a surface so flat that if you scaled it up to the size of a football field, the biggest bump would be a fraction of an inch tall. That level of perfection matters because the features you're going to print on this surface are impossibly tiny, and any imperfection in the underlying surface would ruin everything. Now, you coat this wafer with a thin layer of a special material called photoresist. Think of photoresist like a very sophisticated version of the coating on photographic film. It's a chemical that changes its properties when light hits it. In some types, called positive photoresist. The areas exposed to light become soluble. They can be washed away. In other types, negative photoresist, the exposed areas harden and the unexposed parts wash away. Either way, the principle is the same. You're using light to create a pattern. So you've got your wafer coated in photoresist. Now you need a pattern to project onto it. That pattern comes from something called a photo mask, or just a mask. Sometimes people call it a reticle. This is essentially a stencil, a plate of glass, with an incredibly precise pattern of chrome deposited on it. The chrome blocks light, and the clear areas let light through. The pattern on this mask is a magnified version of the circuit layout you want to create on the chip, typically 4 or 5 times larger than the final pattern, because the optical system in the lithography machine will shrink it down when it projects it onto the wafer. And that optical system, the lithography machine itself, is essentially the most precise projector ever built. Light passes through the mask, enters an incredibly sophisticated lens system, gets reduced in size, and projects a sharp image of the circuit pattern onto the photoresist-coated wafer below. Wherever the light hits, the photoresist changes. Then you develop the wafer, basically wash it with a chemical solution, and the changed photoresist dissolves away, leaving behind a pattern of bare silicon and remaining photoresist that exactly matches your mask design. Now, here's where it gets really clever. That pattern of exposed and protected silicon isn't the circuit itself. It's a stencil for the next step. You might use that pattern to etch away material, or to implant atoms into the exposed silicon, or to deposit a new layer of material only in certain areas. Each of these steps modifies the wafer in a specific way, building up the structure of the transistors and wiring one layer at a time. Then you strip off the remaining photoresist, coat the wafer with a fresh layer, align a new mask with a different pattern, expose it, develop it, and do the next processing step. Layer after layer after layer. A modern chip might go through this cycle dozens of times, each layer adding another piece of the three-dimensional puzzle. Think of it like building a city, one floor at a time, using a series of stencils. First, you lay down the foundations. That's the transistor layer, where you're actually modifying the silicon itself to create the tiny switches. Then you build up layers of insulation and metal wiring above, connecting all those transistors together into functioning circuits. Each layer requires its own mask, its own exposure, its own processing steps. And every single layer has to be aligned with the ones below it to within a fraction of the feature size. We're talking alignment accuracy measured in nanometers. It's like printing a page of text, then printing another page on top of it, and requiring that every letter lines up perfectly with the ones underneath. Except the letters are smaller than a virus. So the whole game, from the 1960s onward, has been about making this photolithographic process work at smaller and smaller scales. And the fundamental limit on how small you can print is determined by the wavelength of the light you're using. This is basic physics. You can't print features much smaller than the wavelength of light that's doing the printing. For the same reason, you can't write your name with a paintbrush that's wider than the letters. The light has a resolution limit, and as you try to shrink features below that limit, the patterns start to blur and smear together. In the early days, chip makers used ordinary visible light, and that was fine when features were measured in micrometers, millionths of a meter. But as transistors shrank through the 70s and 80s, the industry moved to shorter and shorter wavelengths of light. They went from visible light to ultraviolet light, because shorter wavelengths mean finer resolution. By the mid-1980s, they were using a type of ultraviolet light called G-line, with a wavelength of 436 nanometers. Then they moved to I-line at 365 nanometers. Then, in the 1990s, they made the jump to deep ultraviolet light, DUV, first at 248 nanometers using krypton fluoride excimer lasers, and then at 193 nanometers using argon fluoride excimer lasers. Each of these transitions was a massive engineering effort. New light sources, new lens materials, because ordinary glass absorbs deep ultraviolet light, so you need special materials like calcium fluoride and fused silica. New photoresist chemistries, new mask-making techniques. Billions of dollars of research and development just to move to a slightly shorter wavelength of light. And at every step, people predicted that the end was near, that physics would finally catch up, that you couldn't possibly shrink things any further. In the 1980s, serious people argued that feature sizes below 1 micrometer were impractical. In the 90s, they said the same about features below a 1/4 micrometer. And every single time, engineers found a way around the apparent limit, sometimes through brute force wavelength reduction, but increasingly through a bag of astonishingly clever optical tricks that let them print features far smaller than the light itself. One of the most important of these tricks has a wonderful name: optical proximity correction. Here's the idea. When you try to print very small features, the light diffracts. It bends around edges and interferes with itself, and the pattern you get on the wafer doesn't look exactly like the pattern on your mask. Corners get rounded, narrow lines get thicker or thinner than they should be, and features that are close together interact with each other in weird ways. So what engineers started doing was deliberately distorting the pattern on the mask to compensate for these distortions. They'd add little extra bumps and notches to the mask pattern, features that don't correspond to anything in the actual circuit design, so that after the light diffracts and interferes, the final pattern on the wafer comes out correct. It's like a golfer aiming left because they know the wind is going to push the ball right. You pre-correct for the error. And that's just one trick. There's also something called immersion lithography, which showed up around 2006 and was a genuine game changer. The idea is beautifully simple in concept, even though it's fiendishly hard in practice. Instead of having air between the lens and the wafer, you fill that gap with ultra-pure water. Water has a higher refractive index than air, which effectively shortens the wavelength of the light as it passes through, giving you better resolution without actually changing your light source. It's the same 193 nanometer laser, but the water makes it behave as if it were closer to 134 nanometers. This one trick extended the life of 193 nanometer lithography by years, pushing it far beyond what anyone thought possible. But even with all these tricks, the optical corrections, the immersion, and several others we haven't even touched on yet, there's a point where 193 nanometer light simply cannot be pushed any further. And the industry knew this was coming. They'd known for decades, actually, and they'd been working on the next solution for just as long. The problem was that the next solution was so technically ambitious, so outrageously difficult, that many people genuinely believed it would never work. It required generating a type of light that barely exists in nature, building mirrors polished to the precision of individual atoms, and operating the whole system inside a near-perfect vacuum. The engineers who finally made it work spent the better part of 30 years trying, and the machine they built is arguably the most complex device ever manufactured by human beings. It's called an EUV lithography scanner, and it's made by a single company in the entire world, ASML, a Dutch firm headquartered in Veldhoven, a quiet town in the south of the Netherlands that most people have never heard of. And yet, Without ASML in this one machine, none of the advanced chips in your phone, your laptop, the servers running your streaming services, none of them could exist. That's an extraordinary amount of technological power concentrated in one place, and the story of how it got there is one of the wildest in all of engineering. So let's talk about EUV. Those letters stand for extreme ultraviolet, and the extreme part is not marketing hype. The wavelength of EUV light is 13.5 nanometers. Remember, the previous generation was working at 193 nanometers, and even that required immersion tricks to behave like 134. Now we're talking about 13.5. That's more than 14 times shorter. And in lithography, shorter wavelength means you can print finer features, which means more transistors, which means faster, more powerful, more efficient chips. So the motivation was clear. The problem was everything else. Here's the first challenge, and it's a big one. You can't generate 13.5 nanometer light the way you generate other kinds of light. You can't just build a laser that outputs it directly, at least not with enough power to be useful in a factory. The way EUV light is actually produced sounds like something out of science fiction. Inside the machine, there's a chamber where tiny droplets of molten tin, we're talking about 50,000 droplets per second, fall through a vacuum. Each droplet is about 25 micrometers across, roughly the diameter of a thin human hair. And as each droplet falls, it gets hit by a pulse from a high-powered carbon dioxide laser. Not once, but twice. The first pulse flattens the droplet into a tiny pancake shape, which optimizes its geometry. Then a second, much more powerful pulse vaporizes it, heating the tin to around 500,000 degrees. That's roughly 40 times hotter than the surface of the sun. At that temperature, the tin atoms lose many of their electrons and become a plasma, and that plasma radiates light at a range of wavelengths, including the precious 13.5 nanometers. Think about that for a second. You're vaporizing 50,000 tin droplets per second with a laser, creating a miniature star inside a vacuum chamber, and harvesting one very specific wavelength of light from the resulting plasma. And this has to happen with extraordinary precision and reliability, hour after hour, day after day, in a semiconductor fabrication plant. The engineering tolerances involved are almost incomprehensible, but generating the light is only the beginning of the problem. Here's the thing about EUV light. It gets absorbed by almost everything. Air absorbs it. Glass absorbs it. Any conventional lens material absorbs it. This means you can't use any of the refractive optics that lithography had relied on for decades. No lenses at all. Instead, the entire optical path has to use mirrors, and these mirrors have to be extraordinary. They're made from alternating layers of molybdenum and silicon, each layer just a few nanometers thick, stacked up in what's called a multi-layer coating, about 40 pairs of alternating layers. This creates a kind of Bragg reflector that can bounce EUV light rather than absorbing it. But even with this clever design, each mirror only reflects about 70% of the light that hits it. The rest is absorbed. And there are multiple mirrors in the optical path, typically around 11 of them between the light source and the wafer. If each one reflects 70% and you multiply that out over 11 mirrors, you end up with only about 2% of the original light actually reaching the wafer. 2%. Which is why you need such an incredibly powerful light source to begin with, and why those tin droplets have to be vaporized with such ferocity. And the surface quality of these mirrors? This is where it gets genuinely mind-bending. The mirrors have to be polished to a smoothness measured in fractions of a nanometer. The specification is typically less than 50 picometers of surface roughness. A picometer is a trillionth of a meter. To put that in perspective, if you scaled one of these mirrors up to the size of Germany, a country roughly 900 kilometers across, the largest bump on its surface would be less than a millimeter tall. That's the level of perfection we're talking about. A company called Zeiss, the famous German optics manufacturer, makes these mirrors, and they represent some of the most precisely shaped objects in human existence. Now, because EUV light is absorbed by air, the entire beam path inside the machine has to operate in a near-perfect vacuum. And the mask, the reticle that carries the chip pattern, also has to be reflective rather than transmissive. In older lithography, light passes through the mask. In EUV, the mask is itself a multi-layer mirror with the pattern defined on its surface, and that mask has to be kept absolutely free of contamination, because even a single particle a few nanometers across can create a defect in the chip pattern. Protecting EUV masks from contamination turned out to be one of the hardest sub-problems in the entire development effort, and it took years of dedicated research to solve. So when you add all this up, the plasma light source, the multi-layer mirrors, the vacuum environment, the reflective masks, the contamination control, you start to understand why EUV took so long. The concept was first seriously proposed in the late 1980s. Research programs kicked off at national laboratories like Lawrence Livermore and Sandia in the United States, with significant government funding because the strategic importance was clear. A consortium called the EUV LLC was formed in 1997, bringing together Intel, AMD, Motorola, and others alongside the national labs. And through the late 90s and the 2000s, progress was agonizingly slow. There were years when people in the industry openly questioned whether EUV would ever be production ready. The light source wasn't powerful enough. The mirrors weren't good enough. The masks kept getting contaminated. Each problem, when solved, revealed three more behind it. ASML shipped its first prototype EUV systems around 2006 and 2010, but these were research tools, not production machines. They could expose wafers, but far too slowly and with too many defects to be useful in high-volume manufacturing. The critical metric is something called wafer throughput, how many wafers per hour the machine can process. And for EUV to be economically viable, it needed to hit at least around 125 wafers per hour. For years, the prototypes were stuck at a fraction of that. The problem kept coming back to the light source. You need enough EUV photons hitting the wafer fast enough to properly expose the photoresist, and the early tin plasma sources just couldn't deliver sufficient power. But the engineers kept pushing. And here's where you see something beautiful about large-scale engineering programs: the way dozens of different teams at dozens of different companies and labs each solve their piece of the puzzle, and gradually the whole thing comes together. Zeiss improved the mirrors. Cymer, a San Diego company that ASML eventually acquired, dramatically improved the tin droplet laser source, pushing its power from around 10 watts in the early days up past 250 watts. Resist chemists developed new photosensitive materials optimized for EUV wavelengths. Mask makers developed better defect inspection tools, and ASML itself, with thousands of engineers, integrated all of it into a machine that weighs about 180 metric tons, contains more than 100,000 parts, and costs somewhere in the neighborhood of $350 million per unit. Some of the latest versions, the high-end AEUV machines, cost even more, over $380 million. EUV finally entered high-volume manufacturing around 2018 and 2019, first at Samsung and then at TSMC for the most critical layers of chips at the 7nm and 5nm nodes. After roughly 30 years of development, 3 decades from concept to factory floor. And when people ask why advanced chips are so expensive, or why there are only a handful of companies in the world that can make them, the EUV story is a huge part of the answer. The barrier to entry isn't just money, it's the accumulated knowledge, the supply chains, the precision manufacturing capabilities that took an entire global ecosystem decades to build. Now, here's something worth pausing on, because it connects back to something we talked about earlier: Moore's law. Remember, Moore's observation was that transistor density was doubling on a regular schedule, and the industry essentially turned that observation into a self-fulfilling prophecy by planning around it. EUV is a perfect example of that dynamic. The industry knew, as far back as the 1990s, that they would eventually hit the limits of 193 nanometer lithography. They could see the wall coming, and so they began investing in EUV decades before they actually needed it, spending billions of dollars on a technology that many thought was impossible because the roadmap said they'd need it eventually. That's the power of having a shared industry target. It coordinates investment across competitors: Intel, Samsung, TSMC. These companies compete fiercely, but they all needed EUV to exist, so they all supported its development in various ways. Moore's law, in a sense, created the economic justification for the enormous R&D spending that made EUV possible. But lithography, as central as it is only one part of how a chip gets made. And this is something that's easy to lose sight of when we spend so much time on the light and the optics and the masks. Because after you've used that light to pattern the photoresist, you still have to actually do something with that pattern. You have to transfer it into the silicon, or into whatever material layer you're working with. And the way that happens involves a whole different set of processes: etching, deposition, ion implantation, chemical mechanical, polishing. Each one a deep engineering discipline in its own right. Let's talk about etching, because it's a good example of how the challenges multiply as features get smaller. The basic idea is straightforward enough. You've got your patterned photoresist sitting on top of a layer of material, maybe silicon dioxide, maybe a metal, maybe polysilicon. The resist has openings where the light exposed it and the developer dissolved it. Now, you want to remove the underlying material in those exposed areas while leaving it intact everywhere the resist still covers it. That's etching. And in the early days, you could do this with liquid chemicals, literally dipping the wafer into an acid bath that would dissolve the exposed material. This is called wet etching, and it works, but it has a fundamental problem. Liquids don't care about direction. They eat sideways just as happily as they eat downward, which means your features get undercut. The material erodes beneath the edges of the resist, and your nice sharp pattern turns into something with sloped, rounded walls. When your features are measured in micrometers, a little undercutting is manageable. When they're measured in nanometers, it's catastrophic. So the industry moved to something called dry etching, or more specifically, plasma etching. And this is where things get really clever. Instead of a liquid, you use a plasma, an ionized gas, inside a vacuum chamber. The wafer sits on an electrode, and reactive gas species are generated in the plasma above it. These ions and reactive radicals bombard the wafer surface. And here's the key part. Because the ions are accelerated by an electric field, they travel in a predominantly vertical direction. They hit the surface going straight down. This means the etching is highly anisotropic. It cuts downward much faster than it cuts sideways, giving you those nice vertical walls that nanometer scale features demand. The specific variant most commonly used is called reactive ion etching, or RIE, and in its more advanced form, deep reactive ion etching, which can carve incredibly high aspect ratio trenches into silicon, deep, narrow channels with nearly perfectly vertical sidewalls. But controlling a plasma etch at the nanometer scale is extraordinarily delicate work. You have to manage the gas chemistry, the pressure, the power levels, the temperature, the timing, and you have to do it uniformly across an entire 300 millimeter wafer, which is about the size of a dinner plate. Any variation in etch rate from the center of the wafer to the edge means some transistors come out slightly different from others. And at these scales, slightly different can mean the difference between a working chip and scrap. The engineers who develop etch recipes, that's what they call them, recipes, like cooking, spend enormous effort characterizing and tuning every parameter to achieve the uniformity and precision that modern chips require. And etching is just one step. After you etch a trench or a via, a tiny vertical hole connecting one layer to another, you often need to fill it with something. Maybe a metal conductor, maybe an insulating material, maybe a thin barrier layer to prevent atoms from migrating where they shouldn't. And the way you deposit these materials onto the wafer, especially into those tiny features, involves its own fascinating set of techniques. And that's exactly where we're headed now. So let's start with the most common family of deposition methods, which falls under the umbrella of chemical vapor deposition, or CVD. The basic idea is beautifully simple in concept, even though the execution gets incredibly sophisticated. You put your wafer inside a chamber, you flow in gases that contain the atoms you want to deposit, and you provide energy, usually heat, sometimes plasma, to drive a chemical reaction that breaks those gas molecules apart and causes the desired material to form as a thin solid film on the wafer surface. Think of it almost like condensation on a cold window. Except instead of water vapor just settling out of the air, you're actually driving a chemical transformation. The gas molecules react, and the product of that reaction is a solid that accumulates atom by atom on everything inside the chamber, but most importantly, on your wafer. Here's a concrete example. Say you need to deposit a layer of silicon dioxide, glass essentially, onto your wafer. You might flow in silane gas, which is silicon bonded to 4 hydrogen atoms, along with oxygen. When those gases meet at the right temperature, they react. The silicon grabs the oxygen, the hydrogen goes away as a byproduct, and you get a thin film of silicon dioxide growing on the surface. By controlling the gas flow rates, the temperature, and the pressure, you can control exactly how thick that film gets, down to just a few nanometers if you need to. Now CVD comes in many flavors. There's thermal CVD, where you just use heat to drive the reaction, typically at temperatures ranging from maybe 400 to over 1,000 degrees Celsius, depending on what you're depositing. There's plasma-enhanced CVD, or PECVD, where you ignite a plasma in the chamber to provide the activation energy instead of relying purely on heat. This is really useful because it lets you deposit films at much lower temperatures, which matters a lot when you're building up the later layers of a chip. See, by the time you're wiring up the metal interconnect layers, and we'll get to those, you've already got transistors and other delicate structures underneath. You can't blast the whole wafer at 900 degrees without damaging what's already there. So PECVD lets you deposit quality films at maybe 300 to 400 degrees, which the underlying structures can tolerate. But here's the thing about CVD. Even plasma-enhanced CVD, it has a limitation that becomes really painful as features shrink. When you're trying to deposit a film into a very narrow, very deep trench, or via, the gas molecules have to find their way down into that hole. And at a certain point, the hole is so narrow and so deep that the gas molecules tend to react and deposit on the top edges before they ever reach the bottom. You end up with a film that's thicker at the top of the trench and thinner at the bottom, or worse, the top pinches closed before the bottom is filled, leaving a void, a tiny air bubble sealed inside your chip. And voids are bad. They increase electrical resistance, they can cause reliability failures, they're just not something you want hiding inside your interconnects. This is where a technique called atomic layer deposition, ALD, becomes absolutely essential. And honestly, ALD is one of those ideas that's so elegant, it makes you smile when you really understand how it works. The concept was actually developed back in the 1960s and 1970s by a Finnish physicist named Tuomo Suntola, who was originally trying to find better ways to make thin films for electroluminescent displays. He patented the process in Finland in 1974, calling it atomic layer epitaxy. For decades it remained somewhat niche, a curiosity in the thin film world. But starting in the late 1990s and really accelerating in the 2000s, the semiconductor industry realized that ALD was going to be indispensable for the kinds of features they needed to build. So, how does it work? Instead of flowing all your precursor gases into the chamber at once and letting them react continuously, ALD breaks the deposition into two self-limiting half reactions. Here's the sequence. First, you pulse in gas A. Let's call it the first precursor. This gas reacts with the surface of the wafer, but here's the crucial part. It can only react with available bonding sites on that surface. Once every available site has reacted with a molecule of gas A, the reaction stops. It literally cannot deposit more material no matter how much gas you flow, because there's nothing left for it to bond to. The surface is saturated. Then you purge the chamber. Flush out all the leftover gas A and any byproducts. Next, you pulse in gas B, the second precursor. Gas B reacts with the layer that gas A left behind, completing the chemical reaction and forming one atomic layer of your desired material. Again, this reaction is self-limiting. Once every site has reacted, it stops. You purge again, and now you've deposited exactly one atomic layer. One cycle, one layer. You want a film 10 atoms thick? Run 10 cycles. 50 atoms, 50 cycles. The beauty of this self-limiting mechanism is that it gives you two extraordinary things. First, you get angstrom-level thickness control. You know exactly how thick your film is because you're counting layers. And second, and this is the part that really matters for filling those deep, narrow features, you get perfect conformality. Because each half reaction saturates every exposed surface equally, the film coats the bottom of a trench just as well as the top. It coats the sidewalls just as well as the flat surfaces. It wraps around corners, lines the insides of holes, follows every contour of the topography with uniform thickness. No voids, no thin spots, no pinch-off at the top. It's like the difference between spray painting a complicated shape, where the paint hits the front but misses the nooks and crannies, versus dipping the whole thing in a vat of paint so every surface gets an even coat. The trade-off, of course, is speed. A LD is slow. Each cycle deposits maybe 1 angstrom of material, 1/10 of a nanometer. And each cycle takes several seconds because you have to pulse, wait for saturation, purge, pulse again, purge again. So depositing even a few nanometers of film can take minutes, and depositing thicker films takes much longer. For high-volume manufacturing, where throughput is everything, you don't use ALD for thick films. You use it surgically for the critical thin layers where nothing else gives you the conformality and control you need. And one of the most famous applications of ALD in modern chipmaking is for what's called the high-K gate dielectric. Let's talk about that for a second, because it's a great example of how materials, science, and device physics collide. For decades, the insulating layer in a transistor's gate, the thin barrier between the gate electrode and the silicon channel underneath, was made of silicon dioxide. Good old glass. It worked beautifully because silicon dioxide is easy to grow on silicon. It forms a nearly perfect interface with very few defects, and it's an excellent insulator. But here's the problem. As transistors shrank, that silicon dioxide layer had to get thinner and thinner to maintain the gate's ability to control the channel. By the early 2000s, at the 90 nanometer and 65 nanometer technology nodes, the gate oxide had been whittled down to just about 1 to 1.5 nanometers thick. That's maybe 5 atoms. And at that thickness, quantum mechanics starts to ruin your day. Electrons can tunnel straight through the oxide. They don't need enough energy to climb over the barrier. They just quantum mechanically appear on the other side. This tunneling current is a leakage current, and it means the transistor wastes power even when it's supposed to be off. By the time you had 1 billion transistors on a chip, all leaking a tiny bit, the total leakage power was becoming a serious fraction of the chip's power budget. The solution was to replace silicon dioxide with a different insulating material that has a higher dielectric constant, a higher K value. The dielectric constant is basically a measure of how much electric field a material can sustain for a given thickness. A higher K material lets you use a physically thicker layer, which blocks tunneling, while getting the same electrical effect as a thinner layer of silicon dioxide. You get the capacitance you need for gate control without the quantum mechanical leakage. Makes sense, right? Use a better insulator so you can make it thicker without losing performance. The material the industry settled on was hafnium dioxide and closely related hafnium-based compounds. Hafnium is element 72, a transition metal. It sits right below zirconium in the periodic table. Hafnium dioxide has a dielectric constant of roughly 20 to 25, compared to about 3.9 for silicon dioxide. So you can use a layer that's physically 5 or 6 times thicker and get the same electrical behavior. That thicker layer essentially slams the door on quantum tunneling. But here's where ALD comes in. That hafnium dioxide layer still needs to be incredibly thin and incredibly uniform. We're talking maybe 1.5 to 2 nanometers of equivalent oxide thickness, which translates to a physical thickness of maybe 5 to 8 nanometers of hafnium dioxide. And it has to be deposited with absolute precision across the entire wafer, with no pinholes, no thickness variations, no contamination at the interface with the silicon underneath. ALD is essentially the only technique that can deliver that level of control. Intel was the first to introduce high-K metal gate transistors in high-volume production in 2007 at their 45 nanometer node. It was a huge deal, the biggest change in transistor materials in decades, and it was enabled by ALD. Now, there's another deposition technique we should touch on, which is physical vapor deposition, or PVD. This is conceptually much simpler than CVD or ALD. In PVD, you physically knock atoms off a solid target and let them fly across a vacuum and land on the wafer. The most common form is sputtering. You bombard a target made of whatever material you want to deposit, say copper or titanium or tantalum, with energetic argon ions. These ions slam into the target and eject atoms from its surface, and those ejected atoms travel through the vacuum chamber and coat the wafer. It's a bit like throwing billiard balls at a rack. The impact sends balls flying in various directions. PVD is great for depositing metals and certain barrier materials. It's fast, it can deposit very pure films, and it's relatively straightforward to control. But it has its own conformality challenges. Because the atoms travel in more or less straight lines from the target to the wafer, it's hard to coat the bottoms and sidewalls of deep features evenly. So in practice, modern chip manufacturing uses a combination of all these techniques: PVD for some layers, CVD for others, ALD for the most critical thin films, each chosen for the specific requirements of that particular step. And speaking of metals, this brings us to one of the most important transitions in the history of chip manufacturing, one that happened in the late 1990s and fundamentally changed how chips are wired up. For decades, the metal used to connect transistors to each other. The wiring, the interconnects, was aluminum. Aluminum is a good conductor. It's easy to deposit and etch, and the industry had decades of experience working with it. But as chips got faster and interconnects got thinner, aluminum started hitting a wall. Its electrical resistance is higher than copper's, about 40% higher. And at the nanometer scale, that extra resistance means signals take longer to travel through the wires, and more energy is wasted as heat. The interconnect delay was actually becoming a bigger bottleneck than the transistor switching speed itself. So the obvious answer was to switch to copper. Copper is a better conductor, period. But copper presented a terrifying problem that had kept the industry away from it for years. Copper is a fast diffuser in silicon. If copper atoms get into the silicon, into the active transistor regions, they create deep-level traps that destroy the transistor's electrical behavior. Copper is essentially poison to silicon devices, and copper is notoriously difficult to etch using plasma processes. Unlike aluminum, you can't easily pattern copper by depositing a blanket film and then etching away what you don't want. IBM solved both problems in 1997 with a process called the Damascene process, and the name itself tells you something wonderful about how old ideas resurface in new contexts. The name comes from Damascening, the ancient metalworking art practiced in Damascus, Syria, where craftsmen would inlay gold or silver wire into grooves carved in steel to create decorative patterns on sword blades. The semiconductor Damascene process works on exactly the same principle. Instead of depositing copper and then etching it into wires, you first etch trenches into the insulating dielectric layer. Carve the pattern of the wires into the insulation. Then, you deposit a thin barrier layer, typically tantalum and tantalum nitride, using PVD, to line those trenches and prevent copper from escaping into the surrounding material. Then you deposit a thin copper seed layer, also by PVD. And then, and this is the part that surprised a lot of people, you fill the rest of the trench with copper using electroplating. Actual electroplating. The same basic electrochemistry that's been used to plate jewelry and car bumpers for over a century. You dip the wafer into a copper sulfate solution, run a current, and copper ions from the solution deposit onto the seed layer, filling the trenches from the bottom up. Once the trenches are overfilled, you polish off the excess copper from the top surface using chemical mechanical planarization, CMP, which is essentially a very precise, very controlled polishing process that uses a combination of chemical slurry and mechanical abrasion to grind the surface perfectly flat. The result is copper, wires inlaid in an insulating matrix with barrier layers keeping the copper contained and a perfectly planar surface ready for the next layer to be built on top. IBM introduced this in production at their 220 nanometer node in 1997, and the rest of the industry followed within a few years. It was a landmark moment, the first fundamental change in interconnect metallurgy in the history of integrated circuits. And what's remarkable is how many different techniques come together in just that one process sequence. You've got lithography to define the trench pattern, plasma etching to carve the trenches, PVD to deposit the barrier and seed layers, electroplating to fill with copper, and CMP to planarize. Each of those is its own deep engineering discipline, and they all have to work together seamlessly at nanometer precision, billions of times across a single wafer. When people ask why chips are expensive to manufacture, this is why. It's not any one step that's impossibly hard. It's the cumulative orchestration of hundreds of steps, each one demanding its own kind of perfection, all stacked on top of each other in a sequence where a single misstep in step number 200 can ruin everything that came after. That's the real story of chipmaking. It's a symphony, and every instrument has to be in tune. So now that you've got this beautiful copper wiring inlaid in your insulating layer, perfectly flat, ready to go, what happens next? Well, you do it again, and again, and again. Because one layer of wiring is nowhere near enough. Think about it this way. You've got billions of transistors down at the bottom of your chip, all sitting on the silicon surface. Each one of those transistors needs to be connected to other transistors, sometimes to neighbors, sometimes to partners on the far side of the die. And all of those connections have to be routed without crossing each other in ways that cause short circuits. It's like trying to wire up an entire city's telephone network. Except the city has a few billion buildings, and you can only run cables in perfectly straight horizontal and vertical lines. You simply cannot do that in one layer. You need many layers, stacked vertically, with connections running between them. And that's exactly what modern chips have. A modern processor might have 12, 14, sometimes 16 or more layers of metal interconnect stacked on top of each other. The bottom layers, closest to the transistors, have the thinnest, most tightly packed wires, because down there you're making short, local connections between nearby transistors. As you move up through the stack, the wires get wider and the spacing gets more generous, because those upper layers are carrying signals over longer distances or distributing power and ground across the whole chip. The very top layers might have wires that are, relatively speaking, enormous, maybe a few micrometers wide, compared to the hair-thin traces at the bottom that might be only 20 or 30 nanometers across. Each layer goes through that entire damascene process, deposit an insulating dielectric, pattern it with lithography, etch trenches, deposit barrier, deposit seed, electroplate copper, CMP to flatten. And then between each metal layer, you need vertical connections, little pillars of metal called vias that punch through the insulating layer to connect one wiring level to the next. Those vias are made using essentially the same damascene approach. You etch a hole instead of a trench, line it, fill it, polish it. So the full sequence for each level is actually a dual damascene process. You form both the via and the trench in a coordinated sequence, fill them both with copper at once, and planarize. It's elegant, but it means the number of process steps multiplies alarmingly fast. By the time you've built up a full interconnect stack, you might have gone through several hundred individual processing steps just for the wiring alone, on top of all the front-end steps that built the transistors themselves. Here's something that might surprise you. In a modern high-performance chip, the interconnect stack, all those layers of copper wiring and insulation, is actually much taller than the transistor layer itself. If you could look at a cross-section of a finished chip, the transistors would be this thin little band at the very bottom, and towering above them would be this skyscraper of metal layers, getting progressively thicker as they go up. It's like a city where all the buildings are 1 story tall, but the highway overpasses above them are 20 stories high. The wiring dominates the physical structure of the chip. And here's the thing. The wiring isn't just a passive carrier. It actually determines a lot of the chip's performance. As wires get thinner, their electrical resistance goes up. And as wires get closer together, the capacitance between them increases. Resistance and capacitance together create what engineers call RC delay. The signal takes longer to travel down the wire because it's fighting resistance and charging up capacitance along the way. At older technology nodes, the transistors themselves were the bottleneck. They were the slow part. But as transistors got faster and faster with each new generation, the wiring didn't keep up. By the time the industry hit the 130 nanometer node and below, the interconnect delay started to dominate. Your transistors could switch in picoseconds, but the signals were spending most of their time crawling through skinny copper wires. The highway was the bottleneck, not the cars. That's actually one of the reasons the industry switched from aluminum to copper in the first place. Copper's lower resistivity helped, but it wasn't enough on its own. Engineers also had to change the insulating material between the wires. Traditional silicon dioxide has a dielectric constant of about 3.9, and that contributes to capacitance. So the industry started developing what are called low-K dielectrics, materials with a dielectric constant lower than silicon dioxide. Carbon-doped silicon oxide, for instance, might have a K value around 2.7 or 3.0. Some approaches went even further, introducing tiny pores into the dielectric to bring the K value down toward 2.0 or below. Air has a dielectric constant of 1.0, so the more air you can incorporate, the lower the capacitance. But here's the trade-off. Those porous, low-K materials are mechanically fragile. They're basically a sponge at the molecular level. And they have to survive CMP, which involves pressing a spinning pad against them with real force. They have to survive thermal cycling. They have to survive all the chemical exposures of subsequent processing steps. Making low-K dielectrics that were electrically excellent, but also mechanically robust enough to survive manufacturing. That was one of the quieter but really consequential engineering challenges of the 2000s and 2010s. Now, let's zoom out for a moment and think about what we've built so far. You've got transistors at the bottom, billions of them. Each one a tiny switch made of carefully doped silicon with a gate stack on top. Above them, you've got this towering interconnect structure, layer after layer of copper wiring embedded in low-K dielectric, connected by vias, all built up through repeated cycles of deposition, lithography, etching, filling, and polishing. The whole thing sits on a silicon wafer that might be 300 millimeters across, with hundreds of identical chips, called dies, tiled across its surface. At this point, you've been processing this wafer for weeks, maybe 2 to 3 months, depending on the complexity. It's been through hundreds of machines, thousands of individual process steps, and it's worth an extraordinary amount of money. A single 300 millimeter wafer of cutting-edge processors might be worth tens of thousands of dollars, maybe more, depending on the product. But you're not done. Not even close. Because right now, All you have is a wafer full of dies that you hope are functional. And the word hope is doing a lot of work in that sentence. Because here's the reality of semiconductor manufacturing. Not every die on that wafer works. Some of them have defects. A particle of dust that landed on the wafer during one of those hundreds of steps. A slight variation in etching that caused a wire to be too thin in one spot. A void in a copper fill. A gate oxide that's a fraction of a nanometer too thick. Any one of 1,000 things can go wrong. And when you're dealing with features measured in nanometers and billions of components per die, the statistical certainty is that some fraction of your dies will have fatal defects. This brings us to one of the most important concepts in semiconductor manufacturing, and honestly one of the most fascinating from a business perspective: yield. Yield is simply the percentage of dies on a wafer that actually work. And yield is everything. It determines whether a chip is profitable or whether it's a money pit. A new process might start with yields of 30 or 40%, meaning more than half the dies you made are scrap. As engineers identify and fix problems, yields climb. A mature process might achieve 80, 85, even 90% yield. Getting from that initial low yield to a high stable yield is called yield ramp, and it's one of the most intense, high-pressure phases in semiconductor manufacturing. The people who do this work, yield engineers, process integration engineers, they're detectives. They spend their days staring at defect maps, which are plots showing where on the wafer the bad dies are. The patterns tell stories. If the defects cluster around the edges of the wafer, that might point to a problem with how a chemical is flowing in a deposition chamber. If they form a streak across the wafer, maybe a particle got caught on a transport arm. If they're randomly scattered, you might be dealing with particles in the cleanroom air or contamination in a chemical supply. Every defect is a clue, and tracking it back to its root cause through hundreds of process steps is genuinely one of the hardest diagnostic challenges in all of engineering. And the tools they use for this are remarkable in their own right. After certain critical process steps, wafers are pulled out and inspected using specialized metrology and inspection equipment. Optical inspection tools scan the wafer surface with laser light, looking for scattered photons that indicate particles or pattern defects. Electron beam inspection tools, essentially scanning electron microscopes adapted for high-speed wafer scanning, can find defects that are too small for optical detection. There are tools that measure film thickness to sub-angstrom precision, tools that measure the width of lines using scatterometry, where you bounce light off a periodic pattern and analyze the diffraction to infer the dimensions. There are tools that measure electrical properties of test structures built into the scribe lines between dies. All of this data feeds into massive databases, and the analysis often uses machine learning now to find correlations that humans might miss. A yield engineer might discover that dies processed in chamber 3 of a particular etching tool on a Tuesday afternoon have a slightly higher defect rate and trace it back to a maintenance procedure that wasn't quite right or a gas flow controller that was drifting out of spec. The level of statistical detective work is extraordinary. But even after all that inspection and optimization, you still have a wafer full of dies, some good, some bad. And you need to figure out which is which before you cut them apart and put them in packages. This is where wafer-level testing comes in, also called wafer probe or wafer sort. A probe card, which is essentially a circuit board with hundreds or thousands of tiny needle-like contacts, is lowered onto each die in sequence. The needles make contact with small metal pads on the die surface, and automated test equipment runs electrical tests, checking that the transistors switch properly, that the logic gates produce correct outputs, that the memory cells hold data, that the chip can operate at its target frequency. Dies that pass are marked as good. Dies that fail are mapped and will be discarded later. Sometimes a die mostly works but can't quite hit the highest performance targets, and those might be sold as a lower-tier product, which is why you sometimes see the same chip architecture sold at different clock speeds and different prices. Often, the slower, cheaper version is physically the same silicon, just sorted into a different bin based on how it tested. Once testing is done, the wafer gets diced, literally cut apart into individual dies using either a diamond-tipped saw blade or, increasingly, a laser. Each good die then needs to be packaged, and packaging is where the chip meets the outside world. And honestly, packaging might be the most underappreciated part of this whole story. For decades, people treated it as an afterthought. You made the chip. You stuck it in a little plastic or ceramic shell. You soldered it to a board. Done. But packaging has become its own frontier of engineering, and in many ways, the innovations happening in packaging right now are just as consequential as the ones happening in the transistors themselves. So let's slow down and really walk through this. When that tiny die comes off the diced wafer, and we're talking about something that might be the size of your thumbnail, or even smaller, it's incredibly fragile. It's a thin sliver of silicon, maybe 3/4 of a millimeter thick, with billions of transistors and over a dozen layers of copper wiring built into its top surface. Those little metal pads on the surface, the ones the probe card touched during testing, are the chip's only way of communicating with the rest of the universe. Everything the chip does, every instruction it receives, every result it sends back, every bit of power it draws, flows through those pads. And the job of the package is to connect those pads reliably to something much larger and more robust. Something you can solder onto a printed circuit board and plug into a computer or a phone or a car. The oldest and simplest approach was wire bonding. You glue the die face up onto a small metal frame called a lead frame, and then a machine uses ultra-thin gold or copper wires. We're talking wires maybe 20 to 25 micrometers in diameter, thinner than a human hair, to connect each pad on the die to a corresponding lead on the frame. The machine does this with a tool called a capillary, which feeds the wire through, forms a tiny ball at the tip. Using a spark, presses that ball onto the pad with a combination of heat, pressure, and ultrasonic vibration to form a bond, then loops the wire over to the lead and bonds it there too. It's called ball bonding, and a modern wire bonder can do this maybe 15 to 20 times per second. Then the whole assembly gets encapsulated in a mold compound, basically an epoxy resin, to protect it. That's your classic black plastic chip package, the kind you see on circuit boards everywhere. Wire bonding works, and it's still used in enormous volumes today for simpler chips, memory, sensors, all sorts of things. But it has limitations. Each wire is a tiny antenna, a tiny inductor, a tiny source of resistance. When you need hundreds or thousands of connections, and when signals are running at gigahertz frequencies, those little wire loops start to matter. They add delay, they add noise, they limit how much power you can deliver cleanly. And physically, you can only fit so many wires around the perimeter of a die. So here's where flip chip comes in. And this is one of those ideas that seems obvious in hindsight, but was genuinely revolutionary. Instead of bonding wires from the top of the die to a frame, what if you flipped the die upside down and connected it directly, face down, to the substrate beneath it? The concept actually goes back to IBM in the early 1960s. They called it controlled collapse chip connection, or C4. The idea is that you put small bumps of solder on the pads of the die, flip the die over, align those bumps with matching pads on a substrate, and then heat the whole thing so the solder melts and forms connections. When the solder reflows, surface tension pulls each bump into a nice spherical shape and self-aligns the die. It's elegant. The advantage is huge. Instead of connections only around the edges, you can have them across the entire bottom surface of the die in a grid pattern, an area array. That means way more connections in the same footprint. A modern high-performance processor might have thousands of these solder bumps, sometimes called micro bumps when they get really small. And because the connections are so short, just the height of a tiny solder ball, maybe 50 to 100 micrometers, the electrical performance is much better. Less inductance, less resistance, cleaner power delivery. Flip chip became the standard for high-performance processors starting in the late 1990s, and today virtually every CPU, GPU, and high-end mobile processor uses some variant of it. But here's the thing. The package isn't just a passive connector anymore. Modern packages are engineered systems in their own right. The substrate that the die gets flip-chipped onto is itself a miniature circuit board with multiple layers of wiring that route signals and power from the dense bump pattern under the die out to the larger solder balls on the bottom of the package, which are what actually connect to the main circuit board. This substrate might have 8, 10, 12 layers of its own. It redistributes the connections, manages power delivery, and sometimes includes embedded capacitors for decoupling. Little energy reservoirs right there in the package to smooth out the rapid current fluctuations that happen when billions of transistors switch simultaneously. And then there's the thermal challenge. A modern high-performance chip might dissipate 100, 200, even 300 watts or more. All of that heat is generated in a tiny area and has to get out. The package includes a heat spreader, usually a copper lid, that's attached to the top of the die with a thermal interface material and spreads that concentrated heat over a larger area so a heat sink or fan can carry it away. Getting that thermal interface right is critical. Even a tiny air gap between the die and the lid can cause hot spots and throttling. Some high-end packages use indium solder as the thermal interface because it conforms perfectly and conducts heat much better than thermal paste. It sounds like a small detail, but people have spent entire careers optimizing thermal interfaces because if you can't get the heat out, it doesn't matter how fast your transistors can switch. Now, here's where the story gets really interesting and where packaging starts to blur the line with chip design itself. For decades, the way to make a more powerful chip was straightforward. You shrink the transistors, fit more on a single die, and you're done. But as we talked about earlier, that's getting harder and more expensive with every generation. The masks cost more, the yields get trickier, the physics gets meaner. So starting around 2010 or so, the industry began seriously exploring a different path. Instead of making one monolithic die bigger and bigger, what if you made several smaller dies and connected them together inside the package? This idea goes by various names: chiplets, multi-chip, modules, disaggregated design. But the core concept is the same. You break what would have been one giant chip into several smaller pieces, each optimized for its function. Maybe the CPU cores are on one chiplet made with the most advanced, most expensive process node, while the input-output controllers are on a separate chiplet made with an older, cheaper process, because they don't need tiny transistors. They need lots of robust analog circuits. You manufacture each chiplet separately, test them separately, and then assemble them together in an advanced package. AMD was one of the first to really prove this could work at scale with their Zen 2 architecture in 2019. They put multiple CPU core chiplets alongside a separate I/O die in a single package. The core chiplets were made on TSMC's cutting-edge 7nm process, while the I/O die was made on GlobalFoundries' more mature 12nm process. This was brilliant for several reasons. The core chiplets were small, which meant yields were high. Remember, smaller dies mean fewer chances for a random defect to land on your chip. And the I/O die, which needed lots of area for memory controllers and PCIe lanes, could be made cheaply on the older process. AMD got the performance benefits of leading-edge transistors where they mattered most, without paying the cost penalty of putting everything on the most expensive process. But connecting chiplets introduces its own challenges. The connections between them need to be fast, numerous, and energy efficient. If you just connect chiplets through the package substrate, you're limited by the wiring density of that substrate, which is way coarser than the wiring inside a chip. This is where technologies like silicon interposers and advanced bridge dies come in. An interposer is essentially a thin piece of silicon, not a chip with transistors, just silicon with very fine wiring etched into it, that sits between the chiplets and the package substrate. Because it's made with semiconductor lithography, its wiring can be much finer and denser than anything you could put in an organic substrate. TSMC's CoWoS technology, which stands for chip-on-wafer on substrate, uses exactly this approach, and it's become essential for high-bandwidth applications. When you hear about the latest AI accelerators, chips like NVIDIA's big GPU packages, many of them use CoWoS or something similar to connect the processor die to stacks of high-bandwidth memory. And that brings up another packaging innovation that's genuinely wild: three-dimensional stacking. Instead of placing chips side by side, you stack them vertically. High-bandwidth memory, or HBM, is the poster child for this. HBM takes multiple layers of DRAM dies, 4, 8, even 12 layers, and stacks them on top of each other, connected by thousands of tiny vertical conductors called through-silicon vias, or TSVs. A TSV is literally a hole drilled straight through the silicon die, filled with copper, creating a direct electrical path from one layer to the next. SK Hynix, Samsung, and Micron all manufacture HBM this way, and it provides enormous memory bandwidth in a tiny footprint, because instead of spreading memory across a wide area of a circuit board, you're going straight up. The latest HBM3E stacks can deliver over a terabyte per second of bandwidth. That's a staggering number, and it's only possible because of packaging innovation. The memory cells themselves haven't changed as dramatically as the way they're assembled. So you can see how packaging has gone from being the boring last step, stick the chip in plastic, solder it down, to being one of the most dynamic areas of semiconductor engineering. There's a phrase you hear in the industry now: packaging is the new Moore's Law. It's a bit of a stretch, but the sentiment is real. When you can't shrink transistors fast enough or cheaply enough, you find performance gains by being clever about how you assemble the pieces. And all of this, the chiplets, the interposers, the three-dimensional stacks, it all has to work together thermally, electrically, and mechanically. The thermal challenges multiply when you stack dies, because now you have heat sources buried under other heat sources with no direct path to the surface. The mechanical stresses are intense too. Silicon and organic substrates expand at different rates when they heat up, and those mismatches create stress on the solder joints. A package might go through thousands of thermal cycles over its lifetime, heating up every time the chip works hard and cooling down when it idles, and every one of those cycles flexes the connections a tiny bit. Reliability engineers spend enormous effort modeling and testing this, running accelerated life tests where packages are cycled between temperature extremes thousands of times to make sure the joints won't crack. Once a chip is packaged, there's one more round of testing. Final test, sometimes called package level test. This is more thorough than wafer probe because now the chip is in its final configuration, operating at real voltages and frequencies, and you can test things that weren't accessible before, like the quality of the power delivery through the package, the integrity of high-speed serial links, and the thermal behavior under load. Chips that pass final test get marked, sorted, and shipped. And the journey from a cylinder of purified silicon to a finished chip in a box is finally complete. It's a journey that can take 3 months or more, from the moment a blank wafer enters the fab to the moment a finished tested chip rolls off the packaging line. And when you hold one of those chips in your hand, this little square of dark silicon and metal no bigger than your thumbnail, it's almost impossible to believe what's inside it. Billions of transistors, dozens of metal layers, miles of copper wiring thinner than a virus, all built up atom by atom in processes so precise they make watchmaking look like finger painting. But here's the thing. We've spent all this time talking about how chips are physically made, the lithography, the etching, the deposition, the packaging, and we haven't really talked about something equally staggering, which is how anyone decides what to build in the first place. Because before a single photon of EUV light hits a wafer, before a single atom of copper gets sputtered onto anything, someone has to design the chip. And the design of a modern processor is, honestly, one of the most complex intellectual undertakings in human history. That's not hyperbole. A chip with 10 billion transistors has more components than there are people on Earth. No human being can design that by hand. No team of human beings can. So the question becomes, how do you actually design something that complicated? The answer is that you use computers to design computers. And the story of how that became possible is its own fascinating thread in this whole tapestry. Let's go back to the early days for a second. In the 1960s and early 1970s, when integrated circuits had a few dozen or a few hundred transistors, engineers really could design them by hand. They'd sit at drafting tables with rulers and colored pencils, literally drawing the shapes of each transistor and each wire on large sheets of paper. These drawings, called layouts, were then photographically reduced to create the masks used in lithography. It was painstaking, meticulous work, but it was manageable because the circuits were small enough for a human mind to hold the whole design at once. You could look at a chip with 200 transistors and understand every single one, what it did, why it was there, how it connected to its neighbors. But then things started scaling. By the late 1970s, you're looking at tens of thousands of transistors. By the mid-1980s, hundreds of thousands. And suddenly, hand-drawing layouts isn't just impractical, it's impossible. The field that emerged to solve this problem is called electronic design automation, or EDA. And it's one of those industries that almost nobody outside of semiconductors has heard of. But without it, the entire digital world stops. The basic idea is this. Instead of designing a chip at the level of individual transistors and wires, you describe what you want the chip to do in a kind of programming language, and then software tools translate that description down through layers of increasing detail until you end up with a complete physical layout ready for manufacturing. It's like the difference between writing a novel by placing individual ink molecules on paper versus just typing words into a computer and letting the printer figure out the ink. Except the translation from high-level description to physical layout is astronomically more complex than anything a printer does. The languages engineers use to describe chip behavior are called hardware description languages. The two big ones are Verilog and VHDL, both developed in the 1980s. In Verilog, for instance, you might write something that says, essentially, when the clock signal rises, if the input is high, set the output to the stored value +1. That's a behavioral description. It tells you what the circuit should do, not how to build it physically. The first big EDA step is called synthesis, where a tool takes that behavioral description and converts it into a network of logic gates, AND gates, OR gates, flip-flops, multiplexers, that implement the described behavior. This is already a hard problem. Finding the optimal arrangement of gates that performs the function you want, meets your speed requirements, and uses the least power and area. That's a combinatorial optimization problem of enormous scale. The synthesis tools use sophisticated algorithms, many rooted in graph theory and Boolean algebra, to explore the solution space. But synthesis only gets you a netlist, a list of gates, and how they connect. You still need to figure out where to physically place each gate on the chip and how to route the wires between them. This is called place and route, and it's where things get truly wild. Think about it this way. You have maybe 100 million logic gates, and each one needs to be assigned a specific location on the chip, and then billions of connections between them need to be routed through those metal layers we talked about earlier. The dozen or more layers of copper interconnect, without any wires crossing where they shouldn't, without any wire being so long that the signal arrives too late, without any area getting so congested that you can't physically fit all the wires. This is, mathematically speaking, an NP-hard problem. There's no known algorithm that can find the perfect solution in reasonable time. So the tools use heuristics, clever approximation strategies that find very good solutions, even if they can't guarantee the absolute best one. And here's what's really clever. The place and route tools don't just worry about connectivity. They have to account for timing. Every wire has resistance and capacitance. Remember that RC delay we talked about? The one that became the bottleneck around the 130 nanometer node. The place and route tool has to know that if it puts two connected gates too far apart, the wire between them will be too long. The signal will take too many picoseconds to travel, and the chip won't meet its clock frequency target. So, placement and routing are deeply intertwined with timing analysis. The tools run what's called static timing analysis, tracing every possible signal path through the chip and calculating whether every signal arrives where it needs to be before the next clock edge. A modern high-performance processor might have billions of such paths to check. If some paths are too slow, the tool tries rearranging gates, resizing transistors, inserting buffer stages, or rerouting wires to fix the violations. It's an iterative process that can take days or even weeks of compute time on powerful server clusters. Now, you might be thinking, wait, weeks to run a computer program? And yes, that's real. The EDA tools that design cutting-edge chips are among the most computationally demanding software in existence. Companies like Synopsys, Cadence, and Siemens EDA. Those are the big three in this space. They employ thousands of engineers just to build and maintain these tools. And the semiconductor companies themselves employ thousands more engineers to use them. The design team for a major processor, say an Apple M-series chip or an AMD Zen core, might include several hundred to over 1,000 engineers working for 3 to 5 years. The cost of designing a cutting-edge chip at the most advanced nodes, when you add up the engineering salaries, the EDA tool licenses, the mask costs, and the test chips, can exceed $1 billion. That number keeps going up with each generation. And this brings us to something that shapes the entire semiconductor industry in ways most people don't think about: economics. The cost structure of chip making is unlike almost any other manufacturing business. The upfront costs are staggering. A modern leading-edge fab costs $20 to $30 billion to build. TSMC's Fab 18 in Tainan, where they make their most advanced chips, reportedly cost around $17 billion. Intel's new fabs in Arizona and Ohio are projected at $20 billion each or more. Samsung's investments are in the same range. These are among the most expensive factories ever constructed by human beings. But here's the thing about those costs: they're mostly fixed. Once the fab is built and the process is qualified, the cost of making one more wafer is relatively modest compared to the capital investment, which means the economics of chip making are all about volume. You need to spread that enormous fixed cost across as many chips as possible. This is why the foundry model that TSMC pioneered has been so transformative. Instead of every chip company needing its own multi-billion-dollar fab, dozens or hundreds of companies can share one fab's capacity. TSMC makes chips for Apple, AMD, NVIDIA, Qualcomm, MediaTek, Broadcom, and hundreds of others. That aggregation of demand is what makes the economics work, and the mask costs alone tell you something about how the economics have shifted. At older nodes, a set of photomasks might cost a few $100,000. At the 5 nanometer node, a full mask set can cost $15 to $20 million. At 3 nanometers, it's even more. That means if you're designing a chip and you make a mistake, if there's a bug in your design that you don't catch until after the masks are made and the first silicon comes back, you've just burned tens of millions of dollars and months of time. This is why verification, the process of checking that a design actually does what it's supposed to do before you commit to silicon, consumes more engineering effort than the design itself. By some estimates, 60 to 70% of the total design effort on a modern chip goes to verification. Engineers write millions of lines of test code, run billions of simulation cycles, and use formal mathematical methods to prove that certain classes of bugs can't exist. And still, first silicon almost always has some bugs. That's why chips are designed with built-in workarounds, spare circuits that can be activated by software patches, fuses that can be blown to disable defective sections, microcode that can be updated after the chip ships. This economic reality also explains something about the geography of the semiconductor industry that has become one of the most important geopolitical issues of our time. Because the costs are so enormous and the expertise so specialized, the industry has concentrated into a remarkably small number of players. As of the mid-2020s, there are really only 3 companies in the world capable of manufacturing chips at the leading edge: TSMC in Taiwan, Samsung in South Korea, and Intel in the United States, with Intel having fallen behind the other 2 and working hard to catch up. And for the most advanced EUV lithography machines, there is exactly one supplier on the entire planet: ASML in the Netherlands. For certain critical chemicals and materials, Japan dominates. For chip design tools, the United States dominates through Synopsys and Cadence. This concentration means the global supply of the most advanced chips depends on a handful of facilities in a handful of countries, and some of those facilities sit in geopolitically sensitive locations. TSMC's most advanced fabs are in Taiwan, an island that China claims as its own territory. The implications of that geographic fact have not been lost on anyone. The United States passed the CHIPS and Science Act in 2022, committing over $50 billion in subsidies to encourage semiconductor manufacturing on American soil. The European Union launched its own European CHIPS Act. Japan, South Korea, India, everyone is trying to build or attract fab capacity. It's a scramble that reflects just how central these tiny pieces of silicon have become to everything modern civilization runs on. National security, economic competitiveness, artificial intelligence, telecommunications, medical devices, energy infrastructure. All of it flows through chips, and so the race to secure domestic manufacturing capacity isn't really about semiconductors in isolation. It's about sovereignty. It's about making sure that if something goes wrong on the other side of the world, a natural disaster, a military conflict, a trade dispute, your country can still build the things it needs to function. TSMC, for its part, has responded to this pressure by agreeing to build advanced fabs in Arizona, with the first facility expected to produce chips using 4-nanometer technology and a second planned for even more advanced nodes. But here's the thing about building a leading-edge fab in a new location. It's not just about constructing the building and installing the machines. The really hard part is the people. TSMC's fabs in Taiwan benefit from decades of accumulated expertise, a deep local talent pool of engineers and technicians who've spent their entire careers perfecting these processes, and an institutional culture that's almost obsessively focused on yield improvement and manufacturing discipline. Replicating that in a new country with a new workforce takes years. TSMC reportedly brought over hundreds of experienced engineers from Taiwan to train the Arizona teams, and even then, the ramp-up timeline has been slower than originally hoped. Samsung faces similar challenges with its fab expansion in Taylor, Texas. Intel, meanwhile, is investing tens of billions in new facilities in Ohio, Arizona, and elsewhere as part of its IDM 2.0 strategy, an ambitious plan to not only manufacture its own chips at the leading edge again, but also to become a foundry for other companies' designs, directly competing with TSMC. Whether Intel can pull that off remains one of the most consequential open questions in the industry. And then there's China. China imports more semiconductors by value than it imports oil. The Chinese government has poured enormous resources into building a domestic semiconductor industry. Hundreds of billions of dollars through initiatives like the National Integrated Circuit Industry Investment Fund, sometimes called the Big Fund. Chinese companies like SMIC, Semiconductor Manufacturing International Corporation, have made real progress, but as of the mid-2020s, they remain several generations behind TSMC and Samsung at the leading edge. The United States, recognizing the strategic implications, has imposed increasingly strict export controls aimed at preventing China from accessing the most advanced chip-making equipment, particularly EUV lithography machines from ASML. These controls, tightened significantly in October 2022 and again in subsequent rounds, represent some of the most aggressive technology restrictions between major powers in decades. The idea is straightforward. If you can't buy the machines, you can't make the chips. But it's also created a powerful incentive for China to develop its own equipment domestically. And while that's extraordinarily difficult, remember, ASML's EUV machines represent decades of accumulated innovation from hundreds of suppliers across multiple countries. It would be unwise to assume it's impossible given enough time and resources. So that's the geopolitical landscape. It's complicated, it's evolving, and it's a direct consequence of the physics and economics we've been talking about all along. The fact that making a chip requires such extreme precision, such specialized equipment, such enormous capital investment. That's what created this concentration. And the concentration is what created the vulnerability. It's one of those situations where the very thing that makes the technology so powerful, the relentless scaling, the incredible specialization, also makes the supply chain fragile in ways that matter to everyone, not just to people who think about semiconductors for a living. But let's step back from geopolitics for a moment, because I want to talk about where the technology itself is heading and some of the really fascinating challenges that engineers are working on right now. Because even though we've come impossibly far from that first point contact transistor at Bell Labs in 1947, from a single crude device on a slab of germanium to chips containing over 100 billion transistors, the road ahead is anything but straightforward. For decades, the story of chip progress was essentially the story of shrinking things. Make the transistors smaller, pack more of them in, run them faster. Moore's law, that remarkably durable observation that the number of transistors on a chip roughly doubles every 2 years, drove the industry like a metronome. But around the time we reached feature sizes below about 10 nanometers, the nature of the game started to change. You can't just keep shrinking planar transistors forever. The physics won't let you. Electrons start tunneling through barriers that are supposed to be insulating. Leakage current becomes unmanageable. The gate loses its ability to control the channel. That's why, back around 2011, Intel introduced the FinFET, a three-dimensional transistor structure where the channel sticks up like a fin and the gate wraps around it on 3 sides, giving much better electrostatic control. TSMC and Samsung followed with their own versions. FinFETs bought the industry another decade of scaling. But now, as we push toward 2 nanometer and below, even FinFETs are reaching their limits. The next major transistor architecture is something called the gate-all-around transistor, or GAA, and the name tells you exactly what it does. Instead of the gate wrapping around 3 sides of a fin, it wraps around the channel on all 4 sides. The channel itself is no longer a fin sticking up from the surface. Instead, it's a series of thin, horizontal nanosheets. Imagine tiny ribbons of silicon stacked on top of each other, with the gate material completely surrounding each one. Samsung began producing GAA transistors in its 3 nanometer process starting in 2022, and TSMC and Intel have their own versions in development. The manufacturing is, as you might expect, extraordinarily challenging. You have to grow these alternating layers of silicon and silicon germanium, then selectively etch away the silicon germanium to release the silicon nanosheets, then deposit gate material all the way around them with atomic-level precision. It's the kind of thing that would have seemed like science fiction 20 years ago, and honestly, it still kind of feels that way. Beyond gate-all-around, researchers are exploring even more exotic approaches. There's something called complementary FET, or CFET, where you stack an N-type transistor directly on top of a P-type transistor, essentially folding the standard CMOS pair into a vertical stack. This could dramatically increase transistor density because you're using the same footprint for 2 transistors instead of 1. But the manufacturing complexity is staggering. You're building one complete transistor, then building another one on top of it, and both have to work perfectly. The thermal budget alone, meaning how much heat each processing step adds and whether earlier layers can survive the temperatures needed for later steps, is a nightmare to manage. But people are working on it, seriously working on it. And then there are the ideas that go beyond silicon entirely. Carbon nanotube transistors, which use tiny tubes of carbon atoms as the channel material, have been demonstrated in labs and offer tantalizing theoretical advantages. Higher electron mobility, better scaling potential, lower power consumption. A team at MIT built a simple microprocessor from carbon nanotube transistors in 2019, which was a genuine milestone. But the practical challenges of working with carbon nanotubes at manufacturing scale, getting them all aligned in the same direction, ensuring uniform properties, integrating them with existing fabrication infrastructure, remain enormous. Two-dimensional materials like molybdenum disulfide, which is only a few atoms thick, are another area of active research. The appeal is obvious. If your channel material is inherently just a few atoms thick, you might be able to scale to dimensions where silicon simply can't function anymore. But again, we're talking about laboratory demonstrations, not production-ready technology. Not yet. Here's what I find really beautiful about all of this, though. The story of chip fabrication is ultimately a story about human ingenuity confronting physical limits and finding ways around them, over and over again. Every generation, someone says we've hit the wall. We can't go smaller. The physics won't allow it. And every generation, some combination of clever engineering, new materials, new architectures, and sheer stubbornness finds a path forward. Not always the path anyone expected. Not always elegant. Sometimes it's a brute force solution like multi-patterning, where you expose the wafer 4 or more times with different masks just to create a single layer of features because your light source can't do it in one shot. Sometimes it's a conceptual leap, like moving from planar transistors to three-dimensional ones. Sometimes it's an enabling technology that took decades to mature, like EUV lithography, which was first proposed in the 1980s and didn't reach high-volume manufacturing until around 2019. More than 30 years of persistent, patient development by thousands of people. And the other thing worth appreciating is how collaborative and interconnected this all is. No single company, no single country makes a modern chip alone. The silicon might come from a mine in Brazil, be refined in Japan, sliced into wafers in South Korea, coated with photoresist made in Germany, patterned by a machine from the Netherlands using light generated by a process developed in part by a Russian-born scientist working in America, etched using gases from specialty chemical companies scattered across the globe, tested with equipment from yet another set of suppliers, packaged in Malaysia or Vietnam, and finally placed onto a circuit board in China that ends up inside a phone designed in California. The supply chain is a web that spans the entire planet, and every node in that web represents deep, specialized expertise that took decades to develop. Think about that for a second. The device in your pocket or on your nightstand or wherever it is right now, it's the product of essentially the entire world's accumulated knowledge in physics, chemistry, materials science, optics, electrical engineering, computer science, and manufacturing. Every chip inside it carries the fingerprints of thousands of engineers and scientists, most of whom will never meet each other, working in dozens of countries, building on discoveries that stretch back to the quantum mechanical insights of the early 20th century. Planck, Einstein, Bohr, Schrödinger, Dirac, They figured out how electrons behave in atoms. Shockley, Bardeen, and Brattain figured out how to use that knowledge to control current in a semiconductor. Kilby and Noyce figured out how to put multiple devices on a single chip. Generation after generation of lithographers, process engineers, materials scientists, and designers figured out how to shrink those devices from millimeters to nanometers, how to stack dozens of metal layers on top of them, how to package them, how to test them, how to make billions of them reliably enough that you can buy one for a few dollars and expect it to work for years. It's one of the most extraordinary achievements in the history of our species, and it happened so gradually, so incrementally, one node at a time, one process improvement at a time, that most people never think about it. You tap a screen and a map appears. You ask a question and an AI answers. You stream a movie, send a message, check the weather. And underneath all of it, billions of transistors are switching on and off, billions of times per second, moving electrons through channels that are just a few atoms wide, routed through copper wires thinner than a virus, all fabricated in rooms cleaner than an operating theater, on machines that cost as much as a commercial aircraft. So as you lie there, maybe starting to drift off, maybe already half asleep, I hope some of this sticks with you. Not all of it. That would be unreasonable. And honestly, some of it might come back to you at odd moments. Like when you're waiting for your phone to update and you suddenly think about photoresist, or when you see a news headline about TSMC and you remember what EUV light actually is, or when someone mentions Moore's law and you think about Gordon Moore sitting in his office in 1965, looking at a graph with just a handful of data points and extrapolating a trend that would hold for decades. These are good things to carry with you, not because you need to know them to get through your day, but because understanding how things are made, really understanding the depth of thought and effort and creativity that goes into the objects we take for granted, makes the world a little more interesting, a little more wondrous, a little more worth paying attention to. And right now, somewhere in the world, it's the middle of the night in a clean room, and an engineer is staring at a wafer under an electron microscope, checking whether the latest process tweak improved the yield by a fraction of a percent. Somewhere else, a designer is running one more simulation, trying to close timing on a block that's just barely too slow. Somewhere else, a scientist is experimenting with a new material, wondering if this might be the thing that keeps the whole incredible machine moving forward for another generation. They're all part of the same story, the same long, improbable, beautiful story of people figuring out how to arrange atoms in just the right way to make sand think. And that story isn't over. It's still being written, one layer at a time, one transistor at a time, right now, even as you close your eyes and let sleep take you wherever it wants to go.